Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be introducing the Kirchhoff's rules. Now, if you've watched some of my previous videos already, then you've already seen a little bit of Kirchhoff's rules, kind of obliquely, let us say. So today, I kind of just want to introduce them a little bit more formally and then discuss some ideas about sign convention. So that is what you're in for in this video. So the Kirchhoff's rules are actually based on two conservation laws. And what I think I will do here is I will write out each of the two rules, and then I will mention like what is the conservation law upon which they're based, and maybe what's the equivalent in fluid dynamics from Physics 1. Okay, so the first of the Kirchhoff's rules is what's called the junction rule. And what the junction rule says is that the total current, the sum of currents going into a junction, must be equal to the sum of currents coming out of a junction. Okay, so this right here is actually conservation of charge. And for those of you who got to take fluids in Physics 1, or who studied fluids a bit in Physics 1, this rule is basically analogous to the continuity equation or continuity conditions in fluids. So that was the volume flow rate, which we represented by a Q. So if Q is the volume per unit time, then this was analogous to saying that Q1, or Q at one point in your system, and Q2, Q at another point in the system, are equal to each other. Okay, so that is the junction rule. The main sort of boxable equation, if you're wanting to put a little box around something, is this one right here. Current in equals current out. The second of Kirchhoff's rules is what's called the loop rule. And what the loop rule says is that if I sum up all the voltage drops around a closed loop, then those equal 0. I'm going to write this condition as like a little bar that has the condition next to it. So this is as long as you're going around a closed loop. All right, and that's maybe also a boxable equation because that is the loop rule stated. So what is this analogous to, and what is it based on? Well, this is actually energy conservation. So the conservation law is conservation of energy. Remember that voltage drops, the voltage is the potential energy per unit charge, and so a voltage drop across something is essentially how much has the potential energy for each charge changed in moving across that something. It's also how much work the system has done. And so you could think of it in terms of other conservation laws like gravity. But again, if we want to be using something analogous from fluids, this is most nearly analogous to the Bernoulli principle. So Bernoulli's principle was the one that basically relates pressure differences to fluid flow rate, really to kinetic energy and to changes in height of your fluid. But that is your analogous principle from fluids. How do you write the Bernoulli principle? Essentially, it's the pressure at point 1 plus 1/2 of the fluid's density times its speed squared, also at point 1, plus the density times the free fall acceleration times the height at point 1 is equal to pressure at point 2 plus half of, this is basically your kinetic energy term, plus your basically potential energy term at point 2. Now I say basically your kinetic energy, basically your potential energy, P basically is the work. Essentially what it is it's conservation of energy that you've divided the volume out of every term. Okay, but again, the two main points here for the Kirchoff's rules is that the sum of current going into a junction is equal to the sum of current coming out of a junction, and that the sum of voltage drops around a closed loop must equal 0. So pictorially, that might look something like this. The junction rule is applicable to anywhere where your circuit either branches or rejoins. So if I happen to have a point in the circuit in which I have wires doing something like this, where they kind of all meet up at some point, and then I have current flowing in each of the wires. So maybe I have I1 here, maybe I2 is right here, and I3 is here. Maybe I4 is off like this, and I5 is coming off like this, and I6 could be here. Maybe I7 also happens to be coming out like this. Then my junction rule, I just look at which ones of these are going into the junction, so which arrows are pointing towards the junction, and so I just happen to choose 1, 2, and 3 to be that way. So I1 plus I2 plus I3. And then what's coming out of it is 4, 5, 6, and 7. So I4, I5, I6, and I7. And essentially I'm just following is the arrow pointing towards the junction or away from it. So this is current into, and this is current out of. And again, it's very much analogous to that continuity equation. If I take a hose and I hook it up to a faucet, I turn the faucet on, some water comes out of the faucet, and then at the other end of the hose, some water also comes out of the hose. And so if I take the hose and I fill up a 5-gallon bucket of water with it, then I know that 5 gallons of water have to have left that faucet in order for that to have occurred. Now, you can quibble a little bit with this because in the case of this hose water analogy, if the hose is empty, it takes a little while before any water comes out. And so more than 5 total gallons will have come out of the faucet, even if only 5 have come out the other end of the hose, because you have some water left in the hose. So one of the assumptions of fluid continuity is that you don't have stuff left behind, or alternatively that the water flows smoothly and continuously. So maybe you initially had a hose that was full of water, like you've put the little sprayer nozzle on one end, there's already water in the hose, you turn the faucet on and then you press the little sprayer. The amount of water that comes out of the faucet and the amount of water that comes out of the spray nozzle then are equal. So the same basic idea is playing here. The amount of charge that goes into a junction via the currents in is equal to the amount of charge that comes out of that junction via the currents out. The loop rule basically involves setups where you have a complete closed loop. So maybe I happen to have a resistor here, maybe there's a second resistor here, maybe down here I happen to have a battery, and then maybe there's like an internal resistance on the battery, something like this. I guess I don't really need a thing coming in, but in principle I could have something coming in. So via the junction rule, there are no junctions here, or in other words, if this is a junction, then whatever current comes here also comes here. Basically, by convention, we can just kind of draw a current going around like this and say this is current I. Your battery you can represent with epsilon. You might represent the different resistors, R1, R2, R internal. And so my junction rule basically says delta V1, delta V2, epsilon, and maybe delta V little r must be equal to 0. And so you can then apply Ohm's law and get something like I times R1 plus R2 plus little r plus epsilon is equal to 0. And that's a basic way of writing it. Note that this implies that either I or epsilon has to be negative. And so by convention, we typically put some signs in. So there's usually sign conventions that use. I'm going to make epsilon negative for this. In principle, you could have chosen I to be negative and epsilon to be positive here. As long as you're consistent, it will work. So this little thing about conventions basically means I should give you a set of conventions that you can follow for the loop rule. This is not the only convention. It is possible to do it other than the way that I am teaching it. The convention I like to follow is that if in kind of moving around the loop, and if you look at this loop here, moving around the loop, I kind of wrote stuff backwards on this line for moving around it a little bit. I could rewrite it so that we're kind of progressing logically. So I could have like a delta VR and a minus epsilon. In some sense, I'm sort of like starting off here and then kind of like imagining going around the loop in this direction of the current. So I'm just kind of traveling counterclockwise and just taking each element as I get to it. And the convention that I'm using, the consistent convention is if the electric field points in direction of, or points same as the direction that we're progressing around the loop, then we treat the element as positive. If the electric field points in the opposite direction as progression around the loop, then that element can be treated as negative. So let's consider a few different elements by way of example. The first is a resistor. So suppose that I have a resistor and I am progressing around my loop. I happen to go from left to right, and the current is also pointing from left to right. By these conventions, this would be a positive voltage drop. The other way around, you get a negative voltage drop. Likewise, if the current is from right to left and you're progressing left to right, that also would count as a negative V sub R. Now let's consider a battery. For a battery, if my progression takes me through the battery from the plus to the minus terminal, then I count that as a negative EMF. And if I go from the minus terminal to the plus terminal, that's a positive EMF. If I go from the minus terminal to the plus terminal, that counts as a negative EMF. Note that the E fields, if I drew them, would maybe look like this. So with the field, positive, against the field, negative. What about a capacitor? If I go from the plus plate to the minus plate, then that counts as a positive voltage. And if I go from minus to plus, that's a negative voltage. Again, that is consistent with the E field direction. So that's it for